Okay, here we go. Let's get started. Here we go. Ready? Here we go, guys. Ready to start. All right, here we go. So there's the current web work that's open, and then we'll open another one. So there's due Wednesday on we're starting the physics stuff, and physics is the last thing we have before the exam, which is a week from Friday. It's the Friday after we get back from fall break. So we have 4 classes to talk about physics. That's plenty of time, but lots of students find this is like some of the hardest problems in the course, so that's good. So we got some extra time to work on it. All right, so let's lay some physics, just basic physics ground rules down here. And so the first thing is force and work. So what is work? Work is the amount of force applied over a distance. The amount of force applied over a distance. So if you're exerting more force, that takes more work. If you're if you're exerting more force over a further distance, or exerting the same amount of force over a further distance, that requires more work. So that's why the formula is force times distance. Okay, but what if force varies according to a function? How are we gonna, so basically, suppose I'm pushing that that whiteboard across a floor, but the floor is wavy, right? It's wavy, and so sometimes I gotta push a little more force. Sometimes I don't have to push as hard. So as I'm pushing the whiteboard across the room with a wavy floor, function is continually changing. So how am I going to get the total amount of work? The function is continually changing across the distance that I'm pushing, or that I'm applying that force. Okay, he's talking about summation. So this is the answer to this question is a major principle or a major thing we've covered in this class, right? The idea of, yeah, we're going to look at, so we can just look at little bits of work at a time, right? So for over a little short different distance, we can assume a constant amount of force and calculate that little bit of amount of work, and then do that lots of times across the whole distance. And so basically then our total work is sums of little bits of work, right? Same thing over again, right? We've seen this with area, we've seen it with volume, we've seen it with rate of change and accumulation, first and foremost. And what else? We saw it with arc length and little lengths, right? So it's the same principle again. If we want the total work, where the force changes, it has to change continually as we're applying force, then we're going to sum up little bits of work to get the total work. All right, so here's that symbolically, right? Integral of lots of little bits of work. Okay, so we should establish here some differences between metric and English units. So force in metric versus English units. Okay, so this formula F equals ma, this is primarily used for metric units only. Metric units. Why? Because when we talk about mass, we're talking about kilograms, and that's a metric unit. Okay, so when you talk about mass, you're usually in the realm of metric units. The metric unit for, or the English unit for mass is slugs. It's kind of obsolete. It's not really used. Okay, so really when we're talking about mass, that's really in the metric system. It's kilograms or grams, and that's why that's where we use F equals ma. Okay, and then acceleration is in meters per second squared. So when you have this formula, kilograms times meters per second squared, what unit is that? Do you guys know? That's newtons, right? That's newtons. So force in newtons is 1 newton is a kilogram meter per second squared. And so what is this formula? Most of us have heard this formula before, but what is it really about? It's about the fact that if you want to accelerate something, it requires force. That's what this is about. Or if you put an unbalanced force on something, it will accelerate. So there's this partnership of acceleration and force. In order to accelerate something, it requires a force. If you put an unbalanced force on something, it will accelerate. That's what that's about. Okay? And the more acceleration that you want, the higher force that you'll need. Okay? All right, so what about the force of gravity? The force of gravity on an object is called its weight. Okay? So weight is force. This is something we have to practice if you didn't know it already. Weight is a specific type of force. It's the force of gravity on an object. Okay? So then, if we want weight force, we use a specific acceleration, which is the acceleration of gravity, which is the same for all falling objects, and that is 9.8 meters per second squared, or 32.2 feet per second squared. But we really don't use that. We usually don't really use the 32.2 feet per second squared in this formula. Why? Because, again, the F equals mg is primarily in the metric system. Okay, so we won't really use this. Now, if we were doing other types of calculation other than force, then yes, we could use this acceleration of gravity, but won't really use this. We'll only have a need for g when we're in the metric system, and that's the 9.8. So the reason we don't use that is because what about weight force when it comes to English units? What is weight force in English units? What unit do we have? This is pounds, right? So we don't have mass. We just go right to pounds. Everything is in pounds already, so we don't use the mg formula when we're in English units. But when we're in metric units, we may be given the mass, and we're talking about weight force, and then to get the weight force, then we're going to use that mass times 9.8. So we're not really going to use the 32.2 feet per second squared, because the idea of English mass in English is obsolete, and we just start with pounds. We just start with pounds. Okay, so the weight in the metric system, like I said, is newtons, because it's force, right? If weight is a type of force and the units of force is newtons, then in the metric system, weight is newtons, and then, like I said, English is pounds. Sometimes we'll be given kilograms, and we'll need to find out the newtons using the F equals mg. Okay, so this is just a summary of what I said. In the English system, mass is not usually used. All force values and thus weights are given in pounds. So we seldom use the F equals mg in English units, meaning we won't use the 32.2. Okay, and the confusing thing is, so in everyday life, we think of kilograms as weight, just like pounds. We think kilograms is the metric for weight, and pounds is the metric for, pounds is the unit for weight in English. So we need to get out of everyday mode and get into physics mode, which is those are apples and oranges. Mass, kilograms is mass. It's the amount of stuff. That doesn't change no matter what planet you're on. If you're on the moon, Jupiter, outer space, mass stays the same. That's kilograms. Okay? But pounds in English, that is a weight force, so that's dependent on gravity. And so that changes depending on your field of gravity. Right? So if you're in space, you weigh 0 pounds. If you're on the moon, you weigh something like a sixth of what you weigh on Earth. If you weigh on Jupiter, you're a hurting unit. Because you weigh a lot, you weigh like, I don't know, I forget what it is, but how many times this much? Anyone know? Acceleration of gravity on Jupiter? 5 times as much? You weigh a lot more on Jupiter, and you couldn't even move. The weight of your own body would just prevent you. Imagine wearing like a suit that's just all weight all over and trying to move around. That's what it would be like on Jupiter. So apples and oranges, right? So newtons is kilograms is mass, pounds is weight. Okay, so if you want force, you need newtons in the metric system, pounds in the English system. Okay, so this is our, if we're talking about work, then this is going to be our main construct for work. So let's talk about springs. So springs, F is the force to hold a spring at a certain displacement. And that's X, right? So X is the displacement. F is the force to hold it at that displacement. And so it's important to note that X is displacement from natural length. It's not the length of the spring. So if I have the spring here lying on the table, okay, that's its natural length. And then if we come along and grab the end of it and then pull it like this. So what is X? This is X. All right, it's displacement from the natural length. It's not the new total length of the spring. It's how much you stretched it from its natural length. That's what X is. Okay, so this formula relates how far you've displaced it from its natural length to the force to hold it there. Okay, the spring constant then is like the stiffness of the spring, like how hard it is to stretch it or compress it. So like a shock in a car for a car wheel has a very high spring constant. A slinky is like literally a zero spring constant, right? Because there's like it takes no force to stretch a spring, a slinky. Okay, and then everything in between. Okay, so what happens when you start stretching a spring? What about the force to hold it at this displaced length versus this displaced length? What happens as you start to stretch a spring? Can you imagine? It gets harder and it takes more and more force to hold it a further distance, right? So here's this situation where, and that's what this is telling you right here. The higher the displacement is, the further you displace it, X, the higher your force to hold it displaced will be. Okay, so as you stretch a spring then, what happens? The force required to keep stretching it keeps getting greater and greater gradually, right? So if we want the work then to stretch a spring, well, you have a constantly changing force to do that, right? A constantly changing force. The force is getting greater and greater and greater to stretch it. So this is that situation we talked about at the beginning. Okay, so here's an example. So a force of 40 newtons is required to hold a spring that's been stretched from its natural length of 10 to 15 centimeters. How much work is done in stretching the spring from 15 to 18 centimeters? Okay, so we have the spring and it has a spring constant, right? That's a value that stays the same. We're going to need that spring constant. So how are we going to get that spring constant? Well, we need a pair, a displacement and a force, a pair of values together, and that will help us get what K is. Do we have that? So it says a force of 40 is required to hold a string that's been stretched from its natural length of 10 centimeters to 15 centimeters. So that means that. The display. Okay, so the force is 40 to hold it at a displacement of what? 5. Everyone see that? And that's, so we can do this in centimeters. Just do the whole problem in centimeters, that's fine. And normally Newton meters is your workforce, but we can just do the whole thing in centimeters, so 5 centimeters. So therefore the spring constant is, it's easy, 8 newtons per centimeter. What does that mean? Every time you stretch the spring another centimeter, what happens to the force that you need to hold it? increases by 8, right? Every time you stretch that spring 1 more centimeter, the force required goes up 8 newtons. Okay? So now, how much work is done stretching the spring from 15 to 18 centimeters? So as you stretch that spring from 15 to 18, what's happening? The force will continually increase. So the resistance of that spring will continually increase. So we need more and more force to get it the next centimeter. Like we said, every centimeter requires 8 more newtons. So what will be the overall approach, the big picture approach to answering this question? How much work is done in stretching the spring from 15 to 18? We've done a lot, yeah. It's not about time. So even if we took an hour to do it, it would be the same amount of work as if we did it in a second. So it's really not about time. But how have we done problems for a long time now?
So our variable seems to be x, as in how long the thing is displaced, how long the spring is displaced.
Okay.
For where we're at. So we have, I'd say, set up an integral. I guess if we're looking for.
So is that what we do in these problems? We just go right to an integral?
No, I guess f equals 8x. So or y equals 8x. So that would be k. We know is 8. So we can just put that back into the equation there.
Okay. So what is our approach to finding? Right, a typical little amount of work. So a typical little amount of work. There might have been lots of good stuff you were saying there. But we're going to go with our typical little amount of work to start with. And then we'll get to our integral. So what is that? That's like delta W. Okay. And so that is, how do we calculate a little bit of work? We need a constant. So the whole point is, when it's a little bit, we can assume a constant force, but then it has to be over a small distance, right? So our delta W would be F delta X. So if we can assume a constant amount of force for a small enough distance, right? Just like we did the accumulation rate of change, right? We assumed a constant rate of change in order to compute a little bit of accumulation. Is that a hand or no? All right, so our typical amount of work. So what is F? What is F going to be? 8x, right? The force is 8x. And then delta x times, so the force is going to be 8x, however far it's displaced at that moment. And then that force at that particular displacement times a little, we're going to just pull it a little bit further and assume a constant force is required to pull a little further. And so now we want all the work to do that as the natural length, let's see, as we stretch from 15 to 18. So what will that be? So that's our setup. We got our little bit of a work. Now we're ready for, yep, so we're going to do, so now the total work, W equals, we're going to sum up all the little bits of work. So 8x. So what's left is x from what to what? 15 to 18 or 5 to 8? It will make a difference. You'll get a different integral. So should it be 15 to 18 or 5 to 8? 5 to 8, because x is displaced length, right? This is dx. We're in terms of x here, so we need displaced length, 5 to 8. You'll get a different answer if you do 15 to 18. But x is the displaced length, not the actual length. So we need integral 5 to 8, 8x dx. This is an easy version of easy, right? 4x squared. Just going to make sure we got our units right here. So 64 times 4. What is 64 times 4? 256? Is that 156? 156 what? What did we just compute? So work is Newton meters normally, but everything, all our distances were in centimeters. This is Newton centimeters. If you want a Newton meters, 100 centimeters in a meter, so 1.56 Newton meters. Okay, questions on that example? So yeah, so we want to, again, probably could have just written down the integral, that's fine, but especially in these physics problems, when things are going to get complicated, there's going to be a lot going on, it's going to be really advantageous to start off with that little amount of whatever it is, right? That typical amount. And if you can, that's the hard part. If you can get that, then setting up your integral is usually, you just write it down, just got to figure out what the limits are. Questions on the spring example? Make sense? Ask if I lose you. Ask if I lose you. Okay, so here's another example. 20 kilogram chain hangs over 30 meters over the roof. Of a building. So here's a building. It's the best building I've drawn all day. All right, and so then it's going to hang over the roof, and we're going to pull up all 30 of those meters up to the roof. Okay, so we're going to pull it up. So as we're doing that, so I'm going to draw the picture when we're like some part of the way done. So we're going to have some bunch of chain up here. Okay? And then we're going to have some amount of the chain. So it's going to start at 30. But then somewhere along the way, we're going to have, so we're going to call this x. X amount of chain is still hanging over, right? And so the maximum value of x is 30. 0. But the picture then just represents kind of along the way, anywhere along the way, when x, meters of chain are still hanging over the edge. Okay? And so, what are we going to do? So why is this a question of interest? Why isn't it just force times distance? Why can't I just get the force, the weight force of the chain times the distance of 30 meters? Yeah, right. So what happens to the force required to pull this thing up? Decreases, gets less and less. As we get more and more chain onto the building, every time we get a link past us onto the building, it's taking less and less force to get it up there. So that force, again, this force function is a changing function, okay? So what are we going to do? We're going to do our little bit of work, right? So typical work. Typical bit of work. And that's delta W. Again, it's going to be force. So if we just move it a tiny little bit, we can assume a constant force. That's the point here. That we need a constant force in order to calculate work. So all we need to do is make that distance short enough, and we can assume a constant force, and then we can calculate a little bit of work. That's the point. And that's our delta x then. Okay, so what do we need? So we need the force when what? When x meters of chain are hanging over the ground, right? So this is like f of x. When x meters of chain are hanging over the top, what is the force required to hold it there? Right, right. So that force required to hold it is the same as what? The weight of that amount of chain that's fallen down there. Okay, so what do we need? We need a function that gives us the weight of, this is essentially the weight of x meters of chain. What's the weight of x meters of chain? Because that's the force that I'm holding it with or pulling it up a little bit with. Are we going to get that? What is, yeah? So we need, so the force to lift this up a little bit is the same as the weight, right? The force to lift something is the same as its weight. The force to lift something is the same as its weight. So we need the weight of x meters of chain. Yeah, but so, but we, it's not going to be minus, right? It's going to be a proportion. How about in the back? Yeah. Yeah, but it's dependent on x, right? It's dependent on how much we have. Yeah, so we need to find out how much. One way to do this would be how much does 1 meter, what's the mass of 1 meter? What's the mass of 1 meter of chain? If we got the mass of 1 meter of chain, then to get the mass of x meters of chain, we would just do what? Times by x, right? We just times by x. So the mass of 1 meter of chain is, if 30 meters is 20 kilograms, then how many kilograms is 1 meter? 2/3, right? So you take 20 kilograms, there's 20 kilograms for 30 meters, we give you 2/3 kilograms per 1 meter. So each meter is 2/3 of a kilogram of this chain. So now, what's the weight? Oh, but so now this is what? This is mass. Mass, we need a couple things. So we need what? We need the force of x meters of chain. So remember that F equals mg, right? F equals mg. So what, and where g is? So let's get the weight of 1 meter of chain. The weight of 1 meter of chain will be the mass of 1 meter of chain, 2/3, times 9.8. So what's that? That's the weight of 1 meter of chain, because it's the force associated with 2/3 of a kilogram. So we got the mass of 1 meter, and then we got the weight, or the force of 1 meter. So then this then is the weight of x meters, which is what? So if 1 meter weighs 2/3 times 9.8, then x meters weighs 2/3 times 9.8. We have x of those, right? We have x of those meters. That's 1 meter, the weight of 1 meter, times x will give us the weight of x meters. There's our little bit of work. Okay. Did you follow that? Did that make sense? Yeah. Right, it's a vertical, right? This is a vertical thing. So we'll get to some where we're going to need a horizontal and a vertical, and then we'll go back to y this way and x this way. But if you just need one dimension, then I just use x. But if you want to use y, that's the same thing. Then all the x's would be y's. Yeah, but so we'll get to some problems where we're going to need 2 dimensions, and then normally we'll do y vertical and x horizontal. But it's all just preference. You know, there's no need to make it x. You can have any symbol that you want. Yeah. Because kilograms is force. Sorry, kilograms is mass, and work is force times distance. Force is the weight. So mass and weight are 2 different things. So we've got the mass in kilograms. We need the weight in newtons. because that's what the force is. The force to lift something is its weight, not its mass. So we need to get from mass to weight, and then we've got force. Okay, cool. And so then now we're ready to add up all the amounts of work. So what are we integrating from here? We're integrating from what to what? As we lift this chain up, x starts at what and ends up at what? Yeah, so x, as we lift, we're integrating really from 30 to 0. But notice what? You have to notice that. What is dx in this? Which way is dx in this situation? Which way is delta x in this situation? Up, right? How is x defined? X is defined in what? The opposite direction of delta x. You see that? So x is defined positive going down, but we're pulling it up. X is decreasing, right? X is decreasing. So because of that, because our delta x is in the opposite direction of x, we're going to throw a negative sign on this dx. Yeah. No, because that doesn't agree with how we defined x, right? This is x equals 0 here, and then increasing down to there. Right? So that's how I defined x, as increasing from the top of the building going down. My frame of reference is the top of the building is 0, and then because we want to think of x as the length of chain hanging over. We don't want negatives, right? We want to think of x as how much chain is hanging over the building. So it starts at 30 and ends up at 0. Yeah. Right, but then you kind of you have two errors, 2 wrongs are making a right there. If you define x going down like this is consistent with the physics that you're integrating from 30 to 0, and your delta x is in the opposite direction of positive x, so we need a negative. Yes, you'll get the same answer, but it's kind of a integrity issue, right? It's like,
Unless you just define x as going up.
What's that?
Unless you define x as going up, and then
Okay, but then x is not how much chain is hanging over the.
like how much chain you're dropping.
It's like, yeah, exactly.
Is dx always negative if the value for a is greater than the value for b?
Um,
In terms of like the bottom.
no, I don't know. Maybe I've never thought about that. It's negative because the change is in the opposite direction of positive x. That's all you need to remember. Watch out for rules, because I'm not sure if they're always true, and then if you forget the rule, then where are you? So just conceptually, the change is up, x is down. That's opposite. Yeah.
If you made it go x as going up in the positive
Uh huh.
then that would make gravity a minus of a 9.8 would go negative, which would switch the
No. So in this case, the direction of gravity is not coming into play because it's just a weight. So there's no acceleration here. It's just a weight. So that's just a magnitude. So you'd still keep a positive 9.8 regardless of how you did x. Yeah. If it was a moving object, we were talking about acceleration, falling down, and then that would have to do with 9.8 having sign. But
Positive x is also in the direction of gravity, so the force would also be positive.
But you'd still say it was if x was pointing up, you'd still keep the 9.8 positive in this problem.
You'd want to, but if you wanted to consider the direction of the force, then the signs would be different. You might need to be careful. But with this reference frame, gravity would be pointing in the same direction.
Okay. Any other questions? Okay, so let's do something a little same kind of deal, but now the chain holds a bucket and it's spilling sand at a constant rate as the bucket is raised. So same problem. but we're pulling up a leaky bucket. Again, we want to draw a situation, kind of like an arbitrary situation along the way. Okay, and so then the sand is spilling out. Sad day for our bucket of sand. Okay, and then, so again, we're going to define x as the amount of chain hanging over the edge of the building. And so before, we had a decreasing force due to the fact that there was less and less chain. We still have that, but we also have more new factor coming into this that's changing the force as we move, and that's the sand spilling out as we go. Okay, so let's take a look at. So we're interested in say x and the mass. So when x is 30, down here, so here's the 30, okay? When x is 30, what is the mass that we have to support at x equals 30? What is the mass that we have to support? So it's the mass of the chain and the bucket and the sand. So what is that initial mass? So I've got a 20 kilogram chain, the whole thing, and then the bucket and the sand together are 25. So I heard someone say 45. Agree with that? Right? Okay. And then when we get to the top, so the moment just before we got all the chain up and we're just about to get the bucket onto the roof, what is x? 0, right? 0. And now what's the mass? 5. When the bucket reaches the roof, the total mass is 5. No more chain left, and the total mass of the bucket and the sand is 5. So right at x equals 0, and we're just finishing up this task, we got 5 kilograms still to go. Okay, again, we want to look at what? A typical amount of work, right? So our typical amount of work is, again, is our force times a little change in x. And so what do we need now? We need to get this force is what? Dependent on what x is, just like it was before, but now we have this added dimension of the bucket and the sand. So what is the force required to lift a little, just to lift it a little bit when x meters of chain are hanging over? That's what we're saying by f of x. Okay, so this right here, what we've got right here is a situation we're going to see in lots of these physics problems. When x is 30, the total mass is 45. When x is 0, the total mass is 5. And what do we need? We need to know what the force is, which essentially mass is one step away from force, right? One easy step away from force. So essentially, we need what the mass is at any value of x, right? We need what is the mass at any typical value of x between 30 and 0. Okay? And what is that a matter of doing? What have we really got there? Yeah, we've got 2 points, and the relationship we're going to have between those 2 points is, in this case, it says to say the sand spills out at a constant rate, right? So really we have a linear or constant rate of change relationship between x and m. this is a very common theme with these physics problems. We need to know what the mass is for any value of x, and then we'll know what the weight or the force is for any value of x. So this idea of creating a linear relationship is going to be huge for us. So can you do it? So what we want is m in terms of x. Or m equals something with x, a formula for m given the value of x. There's more than one way to do this. You just have to have a way. You just have to have a way to figure out what will m be given any value of x between 0 and 30. What will the corresponding m be if it's 45 when it's 30 and if it's 5 when it's 0? So this is what algebra, advanced algebra or something like this, right? So it's just given 2 points. Can you get this equation that will give you m for any x? For which we can then get the force at any x. So take a minute. Can you do it? And you can talk. You don't have to whisper if you want to consult.
So excited for presentation.
A lot of people just kicking back, looking at the screen. Yeah. 20 plus 25, right? 20 kilogram chain and 25 for the mass. I think it's 45. Okay, so here's a way, and hopefully my Calc 1 students did it this way. What we need is, we need a final value of mass, which we can get by an initial mass plus, remember this? Initial value plus. So the final value of mass would be the initial value of mass plus change in mass. And how can I calculate the change in mass? I got a rate of change of 4/3 times what? The change in x. Remember this? Final value of a quantity is the initial plus the change. That change is by constant rate of change, the constant rate times the change in x. So you should have gotten 4/3 x plus 5. What is that? That gives you the mass for any amount of, the mass of the whole thing when x amount of chain is hanging over. And so then what is f of x? It's going to be the mass times mg. So our mass is a function of x. It's our 4/3 x plus 5. G is 9.8. There's our typical amount of work. There's our little bit of work. Okay, this idea of coming up with, you need to know what a certain quantity is for different situations of a distance or of a location. You've got 2 points, you need to be able to build a linear relationship. However you can do that, there's different ways to do that. Here's one way. Final value, or initial value plus the change, which you can compute through rate of change, through a constant rate of change, right? Rate of change times the change in x. So now the work is, we got our typical amount of work, so the total work is integral from, again, -30 to 0, so positive 30 to 0, 30 to 0 of 4/3 x plus 5 times 9.8. Again, a change in x is this way, opposite of positive x. Yes, please.
Why do you still have that 5 plus in the equation for?
Well, let's test it. So our equation has to make these 2 points true, right?
Yeah.
So when x is 0, what is our mass? Does it work? So when 0, I get 5. And when x is 30, I get 10 times 4 is 40, plus 5 is 45. So that makes this work. When x is 0, I need to get a mass of 5. When x is 30, I need to get a mass of 45. Do you see it? Okay. Other questions? All right, so remember 2 web work assignments, the one that's already been open, and then one more on this initial change and work stuff for Wednesday.